Welcome to today's webinar. The topic today is modeling membrane structure using Rhino, Grasshopper and RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the website, the German and English webinars, newsletters, and so on. I will be the moderator today. The presenter will be Lukas Süle, and I will answer your questions together with Paul Sivolgin, but my colleagues can introduce themselves.
Yes, hello, my name is Lukas. I'm hired here as customer support and product engineer with the focus on the interfaces, and I will present the webinar today. Paul, your microphone is...
Sorry, now you can hear me. Hello, I am Paul Sivolgin, working student at Dlubal, and I support the product development in the area of interfaces. Yeah.
Yes, and you will help me answering the questions. Okay, then we can switch off our webcams that the attendees can see the full screen. Some words to your questions. If you have questions, you can answer them with the control panel on the right side of your screen. You can show or hide it with the arrow here and enter the question here. And Paul and me will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's all from my side. I will hand over the screen to Lukas. Lukas, it's your turn.
All right, thank you, Andreas. You should see my screen now.
Yes.
And I will give you a rough overview about the agenda today. And then I will do the live demonstration, but at first, the first topic should be a presentation of the new features of the Grasshopper interface. With new features, I refer to my previous Rhino Grasshopper webinar. So anything that has been developed from that point in time to now till now is what I call new features. The next step will then be the live demonstration of a modeling of a membrane structure. I will do most of the, let's say, programming in Grasshopper and then the export to RFEM 6. And at the end of the presentation today, I will also give you an overview about the planned features, and then we are done. One note regarding the installation of the plugin, I talked about it in the two previous Rhino Grasshopper webinars. I will not explain it again today. My colleague Paul will, however, post a link into the chat, and this link will explain which steps you have to do to install this plugin. All right, then let's switch into the first topic, the new features of the Grasshopper interface. Again, I listed them here in a PowerPoint. The first new feature is that we can create new cross-sections via the cross-section values. So we extended this component that you can see here on the picture with the information under more, so you can define a new cross-section now via the cross-section values. The next thing that we optimized or implemented is non-linearities for node and line supports, as well as for member hinges. So now we can also control the non-linearities in these elements. Not all of them, I have to say. The diagram, the partial activity options, they have not been implemented here. They would require much more input options, and therefore we support now only the simple non-linearities. We also have new components for line releases. As you can see, one component to create the type, like let's say like a hinge, and then the main component, the line release component, where you can define which elements should be released and so on. Additionally, we have extended the load case and load combination component with the initial state setting. This is required for form finding related analysis, and we also extended the load, the member load and surface load components with form finding related load inputs. So far regarding the latest developed features, I will show you now, I will give you now a live demo of this interface or of this add-in. The focus should be, well, again, showing the logic that we implemented here, and also showing the new features, especially form finding related features. Regarding the structure that I will model during this webinar, I prepared it already here. As you can see, it is like a tent structure. Membranes are used for the roof, and some inclined columns, some tension members. We have, of course, cables here as a boundary for the membranes, a center column, and then also some loads, form finding related loads, but also, for example, snow loads to have a proper, let's say, load combination afterwards. Okay, so this is the structure that I will model. In Grasshopper itself, it will look like this. This is the whole algorithm. I have my Grasshopper geometry on the left, which I will not show today. So this is something I will have predefined. I skipped this part here. What I will show is the connection to the Dlubal, to RFEM, basically using the Dlubal components. So it is divided between model data, where I define materials, sections, members, surfaces, supports, and so on. Then the next chapter, load cases and load combinations. Then we have the third chapter, the loads, of course, just exemplary, not like extensively, just a couple of loads. And finally, then the export to RFEM. All right. This is the final algorithm. I will start with this one here, as I said, where I have only the Grasshopper geometry predefined. I can also show what I have here, like really quickly. You can see Rhino on the left-hand side, Grasshopper on the right-hand side. And as usually, you define parameters in Grasshopper to quickly modify the structure. And I have some parameters here for the height of the center column, for example, or the height of the outer columns. The inclination can be modified. I can change the amount of columns to generate different shapes for my tent. The outer radius can be modified, and so on. So you can imagine anything that can be parametric is parametric in that file. And so I have this here, and the outcome of this algorithm that I have here is, of course, surfaces and lines. Surfaces are these membranes, and then I have various lines for my columns, the center column, my top supporting ring here for the membrane, and so on. Tension members, cables, some collection of nodes for my columns, and then also another collection of nodes for my tension members. So this is what I have predefined. And now the goal is to model or to transfer these elements to RFEM and assign RFEM required properties to them. Now the question is, how do you begin with such a project? Well, I think it's good to take a look at RFEM in such a case. And I will take a look here at the data navigator. In the data navigator, you have like a red line for your project. You have the basic objects. These basic objects are materials, sections, thicknesses, and so on. So these are the first things that you need to define in an RFEM project if you want to model a structure. And then you can continue with members and surfaces and so on. Later on, also load cases and loads. The same procedure or the same steps I have to do in Grasshopper. So I will start in my algorithm with the materials, then the sections, thicknesses, and so on. And to do so, I can call up the Dlubal menu in Grasshopper. Yeah, this will show up when you install the plugin. And then you have these 3 categories: the model data category, load category, and let's say the export import categories, or category with the functions. In the model data chapter, you have here a component for the materials, and yeah, you simply define the inputs and you get the material as an output. I have 2 inputs here now. The numbering could be defined, so the index number of the material and the name. The index number is the same number. We have this in all components. This is the number of your material in RFEM afterwards, 1, 2, 3, and so on. Yeah. So you can and you should assign it. Why, I will explain later. Regarding the name or the material can only be created if you use the exact name in Grasshopper, so that RFEM knows which material you want to assign. As an example, you could, of course, say, I want to create an S235. Doesn't matter, you know what I mean. But the name is not clear for RFEM. It will work, it will create an S235, but we have the same steel grade for, let's say, 10 different standards. Yeah, for the Eurocode with the German annex, we have it maybe for the Netherlands annex, and so on. And therefore, you should be very clear regarding the name. You get the exact name at the moment if you go into RFEM, if you call up the conversion tables, and then you can search for your material in these conversion tables. For example, European Union, steel, and then let's say according to EN 1993-1-1, yeah, the typical S235 for the design according to the Eurocode. And this name here, this would be the full name that you ideally use in Grasshopper. Now it seems to be a bit of work, and I agree, but the work theoretically only needs to be done one time. You save it in a list, yeah, a panel, and you can copy this component into all your projects. You can extend it whenever you need an additional material, and then you have your own small library in Grasshopper. Yeah. And this is what I will use in my project here. I will use this list again and again, and inside this list I have all my materials that I need. How can I select one item of this list? Well, we have the list item component. I'm connecting this list to this list item component, and with the index I can pick, let's say, one item from this list. I will create a small number slider from 0 to 15. And the first material that I want to assign is this class PTFE material. It's a membrane, yeah, let's say a membrane related material. So I use here the index number 12. So this component outputs this material, and I can assign the name to my material component. This is all I need to do. I can copy this whole thing because I want to create one more material, an S235. So I use here the index 0, and I'm already done. Now, the next step would be the generation of my cross sections. Therefore, we have also a component here, this section component, and it follows a similar logic. I have to assign a number to this profile. Yeah, I'm using the slider again. I have to use a name, or I have to assign a name. Same logic as for materials. Yeah, you can use the conversion tables in RFEM to get the full name of the cross section, and then you can copy it or save it in such a list. It's the same. This is what I will do again. Yeah, copy paste the elements that I used before, connect them again, and then just select the cross section from that list that I want. For example, cross section number 12. It's a circular hollow section. Yeah. So this is the name of the material of the cross section, and then the next input would be the material number. I'm highlighting here the number because it's not required, it's not intended to write down the name again in here. you have to assign the index number of the material. And I can do it quite easily. I can simply connect the material component with my S235 to this cross-section component. So this S235 will be linked to this cross-section, but it's only working because I assigned the index number beforehand. Yeah, this line basically transfers only the index number. This is what the component requires. So if you do not assign index numbers, you cannot follow up, or you cannot follow this logic. And what would be the alternative way? If you do not assign the index numbers, you theoretically would have to run one export where you export the materials to RFEM. Then you can check in RFEM, okay, what is material 1, what is material 2, and so on. And then you know the ID numbers, and then you could use a number slider or whatsoever and assign the number to your cross section. But this is not the, let's say, ideal logic. The ideal logic is assigning the IDs beforehand. Okay. So far regarding that logic that we are using here, I will create just a couple more cross sections because we have 4 different ones in here. The second one is cross section number 13 from that list. It's also a hollow cross section, but with different dimensions. I'm increasing the index number, of course. This is important. We cannot import different sections with the same index number. Then I will create an R20 cross section. This is for my tension members. And then one more cross section, number 4. And this is number 15. This is a cable cross section for the boundary of my membranes. Okay, that's all regarding the cross sections. The next step is the definition of a thickness, the thickness I need for my membranes. Yeah, a surface needs to have a thickness assigned to it. This is the new RFEM 6 logic. And therefore I'm creating a thickness here with this component. Quite easy to use. Copy paste the index number, using it again, and then the material number. This is then material number 1, the PTFE material. And there's one speciality. Usually you always have to define a thickness in these components. Yeah, because if you have a concrete thickness, you have to define, is it 100 millimeter thickness, is it 300 millimeter whatsoever. In this specific case, I do not have to assign a thickness simply because this material, glass PTFE type 2, has a predefined thickness attached to it. It is 1 millimeter thick. And therefore I don't have to insert anything in here. Yeah. Okay. So that's all regarding, let's say, these very basic components. Now we can continue with the surfaces and the members. For the surfaces, of course, we have a component, a surface component. It requires the Grasshopper surface input, or here we should assign the Grasshopper surfaces to it. So I'm moving the component to my predefined algorithm. Here I have 7 untrimmed surfaces inside of it, and this is what I will use. So the geometry is based on the Grasshopper geometry, of course. Then regarding the the thickness, I link my thickness that I just created to this input. And then the remaining thing that I have to do is assign the numbers. Now, of course, it is possible to assign 7 index numbers to 7 surfaces. I could create, let's say, a list, a simple list, like this, multilinear data. And then I would have 7 index numbers for 7 surfaces. This, however, works only as long as I have 7 surfaces. And as soon as I would modify my parameters here, you can see this is then, let's say, 10 surfaces and not 7 anymore. And then my list does not work. So I create, let's say, a bit more advanced list using the series component. And the series component should start with the index number 1. It it has a step of 1, so the next number would be 2, and the amount of values is, well, then connected to this parameter that I just showed here in the beginning, to the amount of columns, or basically also the amount of surfaces. And then this component generates always the same amount of index numbers as I have surfaces. And that's it. And then I don't have to care about the index numbers anymore. Regarding the surface, one more setting is required. We have to modify the stiffness type for the surface. It is a membrane and not a, let's say, regular standard surface with bending stiffness. Yeah, it's a membrane. And we can assign such specific settings using value lists. Usually, yeah, this in this small info box, you can also see what kind of input is required. It's an empty integer parameter, but you can see in my description, actually it can be controlled via a value list. So I'm using the value list. I connect it to the stiffness type, and then I can choose the settings that you probably know from RFEM. In my case, type membrane. All right, these are my surfaces or my membranes, and I continue with my beams. For the beams, I have a member component. It follows the same logic. I will start with my outer columns. So these are the lines that are the definition or the defined geometry of my columns. The numbering is identical to my surfaces. I can use the same component. I have 7 lines here, so I need 7 IDs. And for the cross section, I can use the cross section type 1. And that's all I have to define here for this first set of members. Then I create another member component. Let's see if I can fit everything on the screen. Maybe like this. So the center column, this is a specific component. I want to control it specifically here. So I have an additional member component, and the cross section is the same. What's different is, of course, the numbering. I also have to assign a number. I do want to assign a number to this beam, but of course it depends a bit on the numbering that I have before here. Yeah? I already have the index numbers 1 to 7, so I could give it the number 8, but if I change the amount of columns and surfaces, this will not work. So my numbering has to depend on this list. So what I will do is following. I will use a list item component. I connect the list of index numbers to this new component. I say -1 is my index that I'm looking for, which means this is the last item from this list. Yeah, the 7. And then I simply add 1 to this number. And now I have here the index number 8. And whenever I increase the amount of columns, this number will of course be increased +1. So this is my, let's say, little bit of logic that I implemented here into this numbering. And therefore, yeah, I'm good for any other modification of the structure. Now, one more member component. I have here the center, the top ring. And for this, I use the section number 2. And for the numbering, I, let's say, use a similar approach. I create a series again, because I have here multiple lines incoming, 14 lines. So I need 14 additional index numbers. The start point is not 0 or 1. It is again based on this value. So 8 is my last index, +1. 9 would then be the starting point for my new series. And this series depends, or the amount of index numbers depends now on the amount of lines inside that component. What I can do is I can use a list length component. This gives me the length of a list, and I can connect it to my top ring. And now my result is not, let's say, clear. I get here 2 values because the list, it's not actually a list that it's incoming here. It's like a tree-like structure, yeah. So I have to flatten the input first. Now I can see it's 14 values. So my last index is the index number 14, and this is the amount of index numbers that I need for my lines. 14 lines, 14 index numbers. So this is also solved here. And another thing that I have to take care about is if I have here a tree-like input in this component, and here I have a list input, I would, there is this Grasshopper logic that with the combination of lists and tree-like structures and so on. So what I will do here is also I will flatten this input. Otherwise, I get multiple times the members. All right, one more member component here. What else do we have? We have the tension members with the cross section for the tension members. The numbering is quite similar to what I used before. I will reuse these components from the top. I'm taking the last index from this list. I add 1 to it, and then let's say a new series component which starts with this index number, and it is again linked to the amount of columns because it's the same amount of tension members that I have in my structure. And now I have the correct amount of index numbers. The additional option that I define here is that these members should be tension members. So the member type can be modified with this component or with this input. I'm using a value list again, and I assign here type tension. Grasshopper line is linked correctly. Okay, then I copy this whole algorithm and relink it. The series, so I will use the same procedure for my numbering. These lines should be now cable lines, and I also have to relink the Grasshopper line input. I want to use this component for my cables. So my cables are the input for this. The numbering is reassigned, and I have cables. Yeah, so this is working, and now all my members are defined. In the next step, I want to define the nodal supports. They are of course also required. Again, I have a component for them. I have to link my Grasshopper nodes into this component. I have them here. Yeah, these are the nodes on the bottom of my columns. And then I could assign index number to it, but I don't need it. Yeah, it's not important. I will not link this component to any other component except the export component. So the numbering will automatically be defined afterwards. And I don't care what the index number is, so I leave it empty. Regarding the definition of the nodal support, we have here some, where is it written in? Yeah, it's written here also in this small info box. In case a support is free in a certain direction, you would enter the value 0. In case it is fixed, so it could not move in this direction, you use the string INF for infinity. And anything else is a value in Newton per meter. So I will fix my supports in specific directions and also about the rotation for the rotation about this global Z axis. Okay, so this is fine. And then I have one more set of nodal supports, and here I want to show a different option. My nodes are those nodes. Yep. And maybe to show it quickly here in Rhino. So the first set of nodes were for the column basis, for the bottom part of my columns. And now I define also supports for my tension members that are which are these inclined members here. And I want to rotate my nodal supports in a way that they always, or that at least one local axis of this nodal support is directed into the direction, in the same direction as the member is directed. So I want to have the support forces in one value and not spread over 3 different vectors. I think you know what I mean. And therefore I need to rotate my support. Before I do so, I will support it properly. So in X, Y, and Z, it should be supported. And the rotation can then be controlled via the options under more. We have here these new options that I explained, or that I showed in the very beginning of this webinar. Non-linearities for nodal supports, including the friction values. And if I want to rotate a nodal support, I have to deal with some inputs, and let me show them before in RFEM so you understand why it is as it is. If I modify such a support, you can see if I want to have it directed into a specific direction, I have to activate it here. So I have to set it active, and then I can define the type of the rotation. Should it be directed to a node? Should it be parallel to the coordinate system of a line or a member? And in case I use a member, I have to assign the member index number. And the same logic we have in Grasshopper. So I have here the direction type input, which the specific direction input. This is a Boolean toggle. I can control it via a Boolean toggle, yes or no. Yes means, I want to have it directed into a specific direction. This is this check that I have to set in RFEM. Then I have a value list for the direction type. Here I can define, should it be directed to the node, or the same options that I have in RFEM. And in case I want to direct it to a coordinate system of a member, I have, of course, to use the member number input to link it properly. And for the member numbers, I can simply use the members that I defined here. Because I assign the index numbers, I can easily connect both elements with each other. So the index numbers of the members will be transferred to this component, and then it's working fine. Again, we have to be careful here. Tree like data structure, list structure, I will flatten this input. All right, so this is all I need to do to rotate a member. And now we are finished with this first topic. Let me quickly group it so it looks a bit better. Maybe like this. All right. So what is the next step? The next step would be the definition of load cases and combinations. For this, we have this left group of elements here. I can easily create a new load case with this component. What do I have to define? I can assign an index number to my load case, the name if I want. It's optional. A static analysis setting and the action category. The static analysis setting is maybe not so, let's say, well known, but you use it every time you create a new load case. The static analysis setting is, should the load case be calculated according to first series, large deformation theory, third order, second order, first order. This is the static analysis setting that we can define, and we have to define it also in Grasshopper. Otherwise, the load case does not know according to which theory it needs to be calculated afterwards. So this is why I have to start with the static analysis setting. This is my first element that I usually define here. I assign an index number to it, and via the value list again. So the value list is the component in this plugin. With this component, I can control, should it be linear, second order, or large deformation analysis. And then I can simply assign it to this load case component. Again, the load case gets an index number, so I can reuse it afterwards. For example, for load combinations. The name, well, we start with the dead loads. It's optional. Anyway, I assign it here. And then we only need the action category now. Well, as minimum requirement, the action category, yeah, is it a permanent load case, variable load case, in case it's like live load, different groups for Eurocode and so on. And you can assign the action category using this load case classification component. This load case classification component is like a little library. You select the code that you're using in your RFEM project. So this code that you select here should be identical to the code that you define here in the standard one group, yeah, EN 1990. If you use a different code, you should also modify the RFEM standard in your file. Otherwise, it's not working. And then you can choose from a list of action categories. Is it permanent? Is it pre-stress? Is it imposed loads? And so on. And in my case, it's a permanent load case. So I can connect my action category with this input, and then I'm done. So it's generating the string that is expected in that input. And it's quite complex string, so nothing you will remember. Therefore, we created this component. Yeah. What else do I have here as settings? I can activate the self-weight of my structure inside this component. I can say it should act in positive Z direction. And well, as an additional setting, I do not want to solve this load case afterwards. I'm not interested in those results. I'm only interested in the results of my load combinations. So yeah, I will simply deactivate it for the calculation. Saves a bit of time afterwards. Okay, second load case, we have 3 in general, so it will not take much longer. I can copy here my index number list slider, actually, then the load or load case. Oh, sorry, wrong component, my bad. I want to create a different load case. This is what I want to do. Index number is number 2. The name could be form finding, in short, form finding. And then static analysis setting is again this one here. Action category is then in 1990, and pre-stress. Yeah, pre-stress is the action category that we use for, let's say, the form finding. I connect it to it, and then I'm done. Yeah, okay. I will create one more load case. There's no load case in this time. Simply to have some proper load combination afterwards. The name is snow. And again, static analysis setting. And the action category from that list, I will take snow smaller than 1000 meter. Okay. I will also deactivate this load case. I don't want to have the results of my snow loads only. This doesn't make any sense without the form finding pre-stress, without the internal forces. The results are not important, so I will not calculate it. Okay. So far regarding my load cases, I can continue with the load combination. But before I do so, I need the design situation. Yeah, RFEM 6 logic. A load combination always needs as an information according to which design situation it should be calculated, or to which it should be grouped in. So design situations are, for example, the ultimate limit state, or the serviceability limit state, accidental limit states, and so on. So we have to create those ones in advance before we can create the load combinations. This is what I will do in Grasshopper really quickly. I have here a component for design situations. I will only create one. The index number should be 1. The name, I don't care. It's optional. Important is this design situation type. It's, let's say, comparable to the action category. Yeah? The full name of this type is not known to you or me, let's say. It's, again, a complex string. And in theory, I would again use my load case classification component. I select my standard group here, and then I would select the design situation type, and I would get the correct string for my, or let's say, ultimate limit state design situation. But the library behind this component is in that case not correct. We will fix it hopefully soon. And so I need a different way to get this name. I have it here in my predefined component. I got the description by simply importing an existing design situation from RFEM into Grasshopper. Yeah, so we have an import component. You can import data from RFEM into Grasshopper. You can then, let's say, you can then split these information up into these subcategories. And then you can also, let's say, extract. Let me move this a bit away. You can then extract, let's say, the design situations by changing here from assemble to extract. And here you would get the design situation type string for the design situations that you defined here in RFEM 6. And this is the way how I got this string. So it's easy to reproduce, and I will simply use it now. I will simply connect this small data component with the description inside to this component. Okay, so far regarding the design situation, it can easily be created, and now I can define my load combinations. Again, we have here 2 components for that. We have the general load combination component. This has as theoretical input the index number. In that case, it's optional. The combination name, it's also optional. The items, this is what I get from this second component. So this is basically the combination of load case number and factor. Yeah, load case number 1 with the factor 1.35, load case number 2 with the factor for 1.5, for example, for live loads, and so on. The static analysis setting number, well, we know where we get this from. Yeah. And the design situation number, this is what we just created, design situation. And now I have to define, or I have to specify my load combinations. Yeah, load combinations are always a combination of load cases. So I have to define the load case number and the factor for it. My first combination could be 1.35 multiplied by load case 1. Yeah, the basic permanent load combination, let's say. So how can I do it? I will create a panel. Inside that panel, I will mention load case index number as a list. So this is my load case number 1. And then it should be multiplied with the factor 1.35. And then I would have 1 load combination. A simple one, but I have 1. And if I want to create additional load combinations, I can simply create additional lists. Yeah, the second load combination could be load case 1 and load case 3. So dead loads plus snow. And in this second combination, I have the factors 1.35 and 1.5. So like this. But now I cannot simply connect all lists into this input and all lists into this input. It would be an incorrect combination of lists afterwards. I have to use the entwine component from Grasshopper. Yeah, this is basically grouping my inputs in a tree-like structure. and then I can combine the right, the right groups with the other right group. Yeah, so now it's combining this list with this list and this list with this list. Yeah. Okay. Regarding the load combination, I have to define some additional settings. As we are talking here about a membrane structure, or where at least a structure where form finding is a topic, I want to use the initial state of my form finding load case in the load combination. Yeah, so I can activate this initial state using a Boolean toggle, and the initial case itself should then be the load case 2, the form finding load case. Oh, this was incorrect. Load case 2. Here. What does it mean? I go into RFEM 6 to show it again. So inside my load combinations, I want to consider the initial state from this form finding load case, yeah, where I define the pre-stress of my membrane and the sag of my cables, and these strains and deformations, they should be used as a basic, as an initial state for the calculation of these combinations. And this is the same procedure that I use in Grasshopper. Yeah, I activate this initial state using a Boolean toggle. I say yes, and then I define the load case. And now my load combinations are created. Well, as soon as I export them. Now the last topic is the loading topic. Let me quickly group this one as well. Color, any other color, green. And the last topic here will be the loads. Again, just 3 loads that you see how it can be used. And my first load is a member load. I want to define the sag of my cables. Yeah, the cables are limiting my membranes here. Yeah, they are the boundary lines basically of my membranes and between my columns, and they should have a predefined sag. Yeah, they are not straight. This is not. It's not possible basically. Yeah, they should have a certain sag, and this is what I can define using a member load. And the member load can be defined as any other object that I used before. I could assign an index number. I don't need to. The index number will be assigned automatically during the export. And I don't care if it is the number 1 or number 2. Yeah, it's not important, so I leave it empty. The load case number is, of course, important. I have to assign in which load case this load should be placed, and it should be inside the form finding load case. The members on which I want to assign this load to, I also have to link into this component. So where is it? This load should act on my cable members. This is, I have my cable members here, yeah, easy visible via this member type. And I can simply connect the member component with this member number or with this input here. Again, that's why I'm doing all this work with the index numbers here. Yeah, I want to use this type of logic, so I have to assign the index number beforehand. And only if I don't care about the index number, because I will not reuse my component in any other component, for example, the nodal supports, yeah, then I will not use the index number. I will not fill it because it's not important for me. RFEM will do it, or the export component will do it during the export automatically. Okay, so now I just have to define my load. Quite easy task. Well, it is a simpler task. You select what kind of load you have via value lists, mostly via value lists. It's a form finding load. It is a very specific load type. So the additional settings for this load will be or can be found under more. It's not what we show as default value. Yeah, let's say for uniform member loads, you will only work with the upper part of this component. If it's getting more specific, you have to use the more option here, and it will show all the other ones. And here I can use again the value list to define that it is a geometric form finding load, it is the definition of the sag of my cable. It should be defined relatively. We can define it absolutely or relatively. We can use a Boolean toggle to control this. Again, this information you can find inside the components. Yeah, you can see in my small text there, Boolean toggle is the, let's say, recommended input way. And I say, yes, I want to have it in a relative input. And then here is the input for the magnitude. And it is 0.1. This means 10% in this case. And so I assign it like this. And it should be a tension related form finding load. Yeah, we also have form finding for compression. Yeah, this is also possible. Yeah, form finding for compression or structures under compression. In this case, I will, however, link it to my tension forces. Okay, so the first load is defined. I will create two more, surface load. This should control the pre-stress in my membranes. And to do so, I have to link it again to my load case, number 2, to my surfaces that I defined here, yeah, because it's acting on all these surfaces. And then just use value lists and values again for the specification of this load. It is a form finding load. It is a radial definition. And then under more, we find the settings for this load. Let's use another value list for form finding method. It is a projected form finding. And the definition is via the stresses and not via forces. And now I can enter the radial and the tangential stress for my surfaces. How does it work? So I want to assign a radial stress in my membranes and a tangential stress. And in the past, we had to modify the internal axis, local axis system of my surfaces. They had to be directed into a specific direction. Yeah, one for radial, one for tangential. And then I was able to assign it. With this new load, it's not required any longer. I can simply say I have a rotation axis, let's say upwards, basically similar to my center column. And then the load knows, okay, tangential means this one, radial means this one. So what I have to do now is I have to, first of all, define the tangential and radial stress in Newton per square meter. Yeah, so Newton, not kilonewton. This is what we expect here as SI units. And then for the axis, I have to define it. I can define it in 2 different ways. Well, actually, I implemented only one way. We have the options point and axis or 2 points. And I minimize the input. I only support 2 points here. And then you can define these 2 points via these 6 coordinates. And the first coordinate is basically 0, 0, 0. It's my base point. Then 0, 0, minus 7.5 for the second point of the axis. And this is how I define my axis. And then I know, or the structure will know what is radial, what is tangential. Yeah. So this is my surface load. I hope, yeah, should be it. And then one more simple load, a snow load on my membranes, just to have some proper loads on my structure. Load case number is now load case 3. Surface number, again, same surfaces. And it is a force uniform. Then in the global set projected direction, yeah, global set projected. The coordinate system definition is a bit specific. You can see it in the description. If you want to refer to the global coordinate system, you should enter here the value 1. For your additional user-defined coordinate systems, you can then use 2, 3, and so on. The index number, in case you referred to the local coordinate system, you have to enter the string local. Yeah, so it's not the same for local and global. You need different types of inputs, but it's working. And then the force is 0.3 kilonewton per square meter, so 300 Newton per square meter. And that's all I need to define for the surface load. All right, this is what I wanted to show for the loads. Quickly group it. What do we have? Yellow. And then the final component is my export component. I can control the export via a Boolean toggle or a button. I like the Boolean toggle. It gives me 2 options. If I set it to true, it will run the export. Then usually I set it back to false. But if I leave it as true, I do have something like a live link. Yeah, whenever I change something, it will run the export again, and RFEM will be updated. And with the button, I would only have one option. Yeah, I can export it once. So I tend to use the Boolean toggle here. The inputs, I have to select, I have to combine all my components to the input. I will use a data component in advance, just to collect it. It is a bit of work. I will have to do it now. I'm sorry, but it takes maybe half a minute to select everything or connect everything actually, but it is required, and then we can run the export afterwards. So in the German webinar, I did this during the generation of my components. Yeah, I always connected it directly to the small data component. Today I forgot about it, so I have to do it at the end. Okay, and now just these few remaining components. Static analysis setting, my load case. Oh, did I just? Oh, where is it? Oh, yeah. Sorry, I somehow did not press Shift. So one more time. So then I really hope I forgot no component. Otherwise, I will use my predefined algorithm and my second Grasshopper file that I have in the background, and we will be able to see the result. Okay, so I connect this to my input. Then regarding the export component, we have a few settings here. Maybe important for you, the unit import, the unit definition. By default, we are using meters as unit. So these coordinates in Grasshopper are by default meters for me. If you are using a different unit, or if you think about a different unit when you define these values, you can modify it using a simple value list, and then you have selection of the units from Grasshopper and Rhino. Flip z-axis is required. I can control it via a Boolean toggle again. What does it do? It basically mirrors my structure in the XY plane. Here my z-axis goes upwards, as you can see. In my RFEM file, it's going downwards. So it should be flipped during the export. Tolerance is not so important. Override is an interesting option that you should think about. I usually always override my structures. So whenever I run an export, the RFEM structure will be overwritten. This is also what we had in RFEM 5 as logic. In RFEM 6, with this component, theoretically, you can also add data to your existing RFEM 6 structure. So when you have a structure open like this, and let's say you model something else next to it, or you want to modify some elements here or add something onto it, it is possible. Yeah. In this case, in Grasshopper, you would set this to false, or you basically do not modify it. I think per default it's false. I set it to true now because I want to override my structure. Yeah, so these are the main options that you need to know about, and then we can run the export. And yeah, I would say we do it. I will put RFEM on the, let's put it on the right-hand side, Grasshopper on the left, RFEM on the right, so we can see what's happening. One thing that we have to talk about regarding RFEM, when you run the export, you always need to have RFEM opened, of course, and you have to have a model open. Yeah, we are not automatically creating new models in RFEM. It needs to be opened in advance. And in this specific case, I'm using form finding related functions. So I need to activate the form finding add-on. Yeah. Otherwise, these options are not available in RFEM and I will get an error for the export. So let's wait until this new file is open. Yeah, so this is my empty, more or less empty file from RFEM, and I will run the export now and hope I made no mistake. Yeah, looking good so far. So you saw it, I set it directly back to false. So whenever I change something, it will not automatically run the export again. Yeah. What do we have here? We have this structure that we expected with the different cross sections, with the rotated nodal supports. Here you can see it's always rotated, at least one axis of my nodal support, the local x-axis, I think it is always directed into the same direction of my tension member. So any forces that I have in my tension member will be in one value in my nodal support. Yeah. What else should I show? Materials are defined, sections. Oh, my cable. No, my cable is not used. I guess I did not assign the cross section of the cables correctly. Let me see. The cross section. Yeah, it's still the cross section from my tension members. I want to use the cross section from the cross section number 4 from the cables. I will run the export again. Okay. And now, yeah, now it's correct. The cable section will be used for these cable members. Okay. I also have my thickness here. Glass PTFE 1 millimeter. Yeah, this thickness comes with the material. I didn't have to assign it. And then I have all my load cases, my dead load case, form finding load case with the loads that I defined. Yeah, with the sag for my cables, and yeah, the pre-stress, the radial pre-stress for my membrane, and also my combination. So anything that I defined has been exported, and I can, yeah, calculate the structure now. The form finding load case, not the load case 1, not the load case 3, as you saw. Yeah, I deselected them for the calculation, and then you get your results. You can analyze your membrane, the basic internal forces in let's say tangential and radial direction. Is there any compression, or is it completely under tension, as it is here and also here? So this is fine, and then you can continue designing your structure. You can use your steel design add-on now for the columns and so on and so forth. Yeah. All right. So far regarding this small live demonstration of the plugin. I hope that I was able to show the logic that we are using here, especially with the index numbers, but also how you can control your components. And yeah, the last thing that I want to mention now is what we have planned for the future. I listed a couple of ideas, and not just ideas, really things that we want to implement. One big topic is, of course, the import of results from RFEM back into Grasshopper. Also, let's say the FE mesh as geometry, maybe. Another big feature is the import of members, including the cross-section outlines. Again, a bigger feature, which needs a bit of development on our side. And then some smaller ones, let's say components to control the FE mesh settings or the start of the calculation, maybe an optimized input regarding rib members, or components for imperfections, as we cannot define them via the Grasshopper interface right now. It will probably take a bit more time to implement such features because I do need a programmer for them. It has to be programmed manually. Other components, as the ones that I use today, such member components like force components, I can basically generate. So whenever you are missing some specific input in here, or maybe an additional component for some input data, I can usually easily generate. But specific options like import of results and so on, this is not a predefined function that we have. We have to program it manually. All right, so far regarding my part, and I will hand it back to you, Andreas.
Okay, thank you, Lukas, for this nice presentation. We are a little bit over the time, but I would like to use the chance to show my screen again before we close the webinar. I would like to show you where you can find the recording under dlubal.com. Under news and events, you will find, or you can find the webinars where are the already planned webinars, and that's today's webinar. You will also get a link in the next days to that page here. And you will find the recording here, the presentation slides here, the Grasshopper file, and the RFEM6 model. If you would like to trial the interface between RFEM6 and Rhino Grasshopper, and you don't have already RFEM6, you can download our free trial version here, both on our website. It's valid for 90 days and it contains all add-ons. If you have questions to our software, or you would like to get a quote or something like that, you can contact our sales team under support and learning. Just fill out the form and they will contact you if you have questions to add-ons, program, and so on. Okay, just a last hint: when you close the webinar or leave the webinar, there's a small survey. Just enter comments there if you want, or you can score the webinar. Just note that the worst score is 1 and the best score is 5. You can enter wishes for future webinars and so on, but you can leave it empty as well. Okay, then I would like to say thank you for your attention. Thanks to Lukas for the presentation. Thanks to Paul for his help by answering the questions. I wish all a nice rest of the day. Maybe we meet each other in another webinar. Bye-bye.